Okay, so we'll be looking at vapor cycles today. But one disclaimer: there's a little background noise because they are doing some work around. But I'll do my best to be as audible as possible. So previously we looked at the gas cycles, and we said for the gas cycles, our working fluid is going to be a gas throughout the entire cycle. And so we don't have a part where the working fluid will condense and become a liquid or anything like that. And for the gas cycles, we said we have three that we are really going to focus on. So we had the Otto cycle, right, which was a spark ignition engine, or that's work with a spark ignition system. We had the diesel cycle that worked with a compression ignition system. Then we had the Brayton cycle, right, which worked with the turbine heater compressor cooler units, right. So these were the three cycles we considered under that. So now we want to look at vapor cycles, and we also spoke about this the last time that for vapor cycles, these are cycles that have working fluids that um would be vapor at a point and liquid at a point. So we want to consider this. So the thing is that you should know how the question is going to be, or you should be able to identify the kind of system you are dealing with from the question. So if you realize that you are dealing with something that's going to be a gas throughout the system, you work with the relations you use for the gas cycles. If it's going to be something that has some kind of liquid that becomes a vapor, like water becoming steam, which is the most common one you would see for today, then you'd work with the relations that we are going to see for today. Right. So at the end of the lecture, you should be able to understand the ideal Rankine cycle and understand why activities such as reheat can improve the efficiency of the Rankine cycle, and then understand the combined cycle and compute its efficiency, and then the need for integrated gasification combined cycle. So today what we'll do is that we would look at the Rankine cycle with a few parameters, right? And then I would make another separate video so that this one doesn't become too long, and I'll use that to talk about the reheat and then the combined cycle, so we would get the understanding. Now, I don't want us to spend too much time on the I don't want to say the word theory. I don't want us to spend too much time on the history, but we'll just brush over it, right? So we know that electricity is important, and there was a point where we're using fuel. We burn fuel so that we can use it to generate steam, and that became a source of energy. So this was something that had been there for a very, very long time. So the most common um well, this was one of the things that we saw for a very, very long time. But then the main thing that happened was the change in the kind of the fuel source, right? But then the whole idea of still generating steam and using that as an energy source continued to persist throughout. They were just looking at more efficient fuel source that they can use to generate that steam, right? So we have an animation here where we have coal. The coal is being burnt, and then the heat generated from the coal is used to generate steam. That steam passes over a turbine, right, which would rotate a shaft that would generate some kind of power from a generator. It's sent through a transformer, and then we get our electricity. And then we have some emissions that would come out as well, right? So this is just the whole idea. We have a fuel source, right, and then we are going to burn that fuel source. The heat generated is used to produce steam from water, right? And then the steam is used to produce electricity. And then we also have a case where we have a geothermal plant. So this is another source of heat. So instead of us burning the fuel, we are using hot water from under the ground, and we are going to use that to generate our steam. And then we can also work with nuclear power plants where we use nuclear reactions to generate heat, and then that heat would also generate steam. So you just realize that we're having different heat sources, but then the main goal is produce steam from water, right? And then we send that steam over a turbine. So there are some very, very common characteristics of all these things. This is another example. There's some very, very common characteristics of all these things. We first start with water. We pump the water to a certain pressure, right? We heat it so that it becomes vapor. It becomes superheated vapor. We pass it over a turbine to generate electricity. Then we now condense it back into water, and then we can repeat the system. So that's what the steam cycle is about, and that's what the Rankine cycle is about, right? So using different fuels, the Rankine cycle is basically an external combustion engine based cycle. So we said for external combustion engines, these are the kind of systems where the heating is done outside the working fluid. So remember when we looked at something like our auto and our diesel cycles, I could have maybe my piston cylinder. So I have maybe a piston cylinder arrangement this way, and then I have my fuel in here, right? I compress it and I burn. This is going to be an internal combustion system because I'm burning the fuel within the system. But in a case like what we see over here, where I'm burning the coal, right, separately from the part that contains the water, the working fluid, then that becomes an external combustion engine. And this allows us to have different kinds of heat releasing mechanisms, right? So we can fluidize some of our materials, we can work with nuclear reactions, we can do so many different things. And then the steam that we generate, we use it to produce some kind of power or some kind of work. Now there are lots of materials on the Rankine cycle that is developed from a Carnot steam cycle. And the challenges in this cycle is we then analyze them and we use them to develop what we call the ideal Rankine cycle. So what we are saying is that we take a Carnot steam cycle, right, and then we use that to develop the ideal Rankine cycle. And we are saying here that this lecture will keep that tradition. So we are going to use that same format. We are going to give a lot of emphasis on newer power plants such as the natural gas combined cycle and the integrated gasification combined cycle. So that will be in the next video that I will do. Now we know that for the Carnot vapor cycle, right, this is going to be our efficiency. So we've seen this before. Now we want to consider a cycle that is using steam, a Carnot cycle using steam. The problem with this is that the turbine is going to have to handle steam. So let me explain that. For us to be able to have a Carnot system, right, this is how our TS diagram is going to be. But realize that our paths are all below, or they are all within the phase envelope. That means that they are going to happen in a place that we have a two phase mixture. We are going to have a liquid vapor mixture there, right? So what I'm trying to say is that for the Rankine cycle, if we are supposed to work with the Rankine cycle to get the maximum efficiency, we need a certain graph like this, right? But then the problem with this is that we are in a two-phase region. So this is a part that has both liquid and vapor. Now, when we get to the part where we have to work with the turbine, the part where we are going to have some kind of isentropic expansion, please take note of that. For the turbine, we have isentropic expansion. For the pump, we have isentropic compression. We spoke about that also when we looked at the gas cycles. So it means that I'm going to have some kind of expansion down here. That expansion is happening in a place where I have a two-phase mixture. I have both liquid and vapor. And that's not going to be good for the blades of the turbine. So usually when we are working with turbines, we are passing gases over the turbine. Those gases should have a very high steam quality, right? So that there's very little moisture in there. Otherwise, the moisture can cause the turbine blades to start to erode, right? And then there's also the problem of we pumping a two-phase mixture as well. So we are trying to pump our fluid, but then we are pumping a mixture of liquid and vapor, which is more difficult in reality, right? So what we can do is that we can shift the graph to look for the best thing to do. So we have a case where instead we don't want, because we don't want to do our compression, or and we don't want to do our um, what's it called, our expansion, right, in the vapor liquid region, we do what we call superheating. So we heat the system to a point where it becomes purely vapor, right? And we also compress to a point where, or we start from a point where we are liquid and we compress to ensure that we are still liquid. So what I mean by that is we are starting out here, we are on the liquid line, so we are liquid. We compress, so we are still in the liquid region, right? When it crosses this path here, that's when it becomes a vapor. When it crosses the critical point here, so we are still in the liquid region. Then we now do some heating to get into the vapor region. So realize that now we are just compressing a liquid. We are not compressing a vapor liquid. So this side is the liquid region. This side is the gas or vapor region. So now we superheat and now it crosses from liquid to gas. So now it's a superheated gas. Now it can pass over my turbine. And because it's passing over my turbine as a superheated gas, it means that I don't have to worry about there being some liquid or moisture content there that can affect my turbine blades. So now I can do my expansion with my turbine here to the point where it now becomes a saturated gas, right? Then I can remove the heat. As for the removal of the heat, it doesn't matter. It's going to be a phase change, so it doesn't matter whether it is in the two-phase region, right? So I would remove the heat and bring it back to the original point. Okay, so I think we can visualize this more with the diagram here instead. So what we are saying is that we are starting out as a liquid, right? And we are going to pump it. So this side becomes a compressed liquid. Now after we do that, we pass it through a boiler and we add heat. So now this side becomes superheated vapor. Then we pass it over a turbine, right? So this side just becomes saturated vapor. Please take note of the various ones. So it's first a liquid, a compressed liquid, a superheated vapor, saturated vapor. Then we remove the heat so that it now starts to condense. Oh, sorry. Okay. It now starts to condense. So this side becomes both liquid vapor, and then it comes back to the point where it is a liquid once again. So this is the TS diagram for that, and this is the diagram that we'll be using for our analysis. Now we are seeing that from point 1 to point 2, we have isentropic compression. So we are compressing it at a constant entropy. Right, so this is for the ideal Rankine cycle. Just like we did for the other cycles, the ideal Brayton cycle, we started with isentropic here, isentropic there, but then we had a question where we had to look at the actual cycle. So then we have to now bring in the turbine efficiency and the pump efficiency, so that we are not working with it as an ideal case, we are working with it as a real case. I would see an example today. Right, then we have from 2 to 3, we have constant pressure heat addition. So from 2 to 3, the pressure is the same, and we are just adding heat. So we spoke about that as well when we looked at the um, gas cycles, and I'll briefly talk about it for the sake of those who might be watching this video for the first time. When we start out at point 1, we have a certain pressure, P1. Now we work with the assumption that there are no pressure losses in our system. So if I pump from P1 to P2 or to point 2, then this is at P2. Now from P2, all I'm doing is to heat it to a vapor, right? So there's a phase change. When there's a phase change, temperature and pressure are constant. So we are just going to heat it. Sorry, we are heating it to a superheated vapor. So pressure is constant, temperature isn't constant because we are heating it to superheated, right? So pressure will be constant. So it means that in the boiler the pressure is the same, and it's going to come out at the same pressure. So whatever is at P2 is the same at P3. So P3 is equal to P2, right? So I can write here that P3 is equal to P2. Then in the same way, after it passes through the turbine, the pressure drops to P4. But from P4, it enters a condenser. The phase changes and it comes back. So once again, we are assuming that the pressure here is going to be the same as the pressure here, right? So our P4 is also equal to our P1. So that becomes a constant pressure heat rejection for the condenser, right? So 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 isentropic expansion, and 4 to 1 is constant pressure heat rejection or heat removal. Now we have our formulas here. You know that they work for a turbine, right? If you are looking at the first law for an open system, remember we started with Q plus W is equal to our M, right? Then maybe we have our H, then our kinetic energy term, then plus our Z. So I think I should remove the G from here instead and make it ZG instead, right? So we have the change in that as well. Then for a turbine, there's no heat. We assume there's no kinetic energy and a significant change in potential energy. So our work term is dependent on the change in enthalpy. So that's what we see here. So for the turbine, we realize that for the turbine, it's between points 3 and 4. So that's why we are using H3 minus H4, right, to do the work of the turbine. There's no heat. The same thing for the pump, right? So it will be H2 minus H1. So that's from point 2 to point 1. Now another thing we can do is that for the enthalpy change when we are working with the pump, we can also use this relation because now we are pumping a liquid, right? And we know that the change in enthalpy can be represented with VDP, especially when our Q is 0. So we have Vp2 minus P1. So that's what we are coming to use here. One thing about this is that usually when you are working with the pump, so please take note of it because we use it when we are solving questions. When you are working with the pump, you are pumping a liquid. Usually the density of liquids are fairly constant, right? They are usually incompressible. So we can assume that if our density is going to be constant, right, then I can assume that my specific volume, that's what I have here, right, is also going to be fairly constant. So my V is going to be 1 over my rho. But what I always advise is that once you know your pressure and once you have the conditions, you can always find your V from the from the steam table, right? If you do not have the means to find it from the steam table or the conditions, no, in fact you have the conditions, but if you don't have maybe the steam table isn't given or you don't have the means or something, you can use this formula and it will still give you a good enough approximation. So I'll actually solve questions with both ways so that you see what I'm talking about, right? Then for the heat coming in with the same law, K plus W being equal to the change in the enthalpy, then the kinetic energy, and then the potential energy, right? We assume that for boilers and condensers, kinetic and potential energy are negligible and there's no shaft work. So our Q is equal to our change in enthalpy, right? So that's what we have here. And for the boiler, it's between point 2 and point 3. That's why we use H3 minus H2. For the condenser, it's between point 4 and point 1. That's why we use H4 minus H1, right? Now the efficiency of a cycle is given by the work done by the turbine minus the work done by the pump over the heat that comes in. So we've seen this expression before. So we can just put in these values that we have here and this becomes the efficiency. We can simplify it further and write it in this form. So the simplification, all that was done was they expanded what we have here. So H3 minus H4 minus H2 plus H1 over H3 minus H2. Then we group H3 minus H2. So it becomes H3 minus H2. So H3 minus H2. Then let me say minus H4 minus H1. So the minus will cater for the negative in front here and then place a negative here all over H3 minus H2. If we should simplify this, we end up with this expression, right? So we have a number of expressions we can use for our calculations. So we have an example here. A steam power plant is proposed to operate between the pressures of 10 kilopascal and 2 megapascal with a maximum temperature of 400 degrees Celsius as shown in the figure. So the figure didn't come, but we'll still draw a diagram to represent it. What's the maximum efficiency possible from the power cycle? So I prepared a separate material so that we can use that to go over the questions separately, right? So we have the same question here. Now this is the TS diagram given to us, but then we can make our own diagram. So we can start out with a pump, right? So we have here, this are point 1, this is point 2, it goes through a heater, this is point 3, it passes through a turbine and comes out, so this is point 4, and then it goes through a condenser and then comes back to point 1, right? So remember, at point 1 we are usually saturated liquid, so that's what we can even see here. At point 2 we are compressed liquid. At point 3 we are superheated vapor, and then at point 4 we are usually a saturated vapor liquid mixture, right? So we've been given the parameters. We know that at point 1 we're told that we are at 10 kilopascal, so 10 kPa. Remember, P1 and P4 are the same, so this is also 10 kPa. Then the higher pressure is 2, so after we compress, this side becomes 2 MPa, and then this side is also 2 MPa. The maximum temperature always occurs at point 3, so that's 400 degrees Celsius, right? So we're looking at the maximum efficiency possible. So we know that for a steam power plant, it's going to be a Rankine cycle. And for the Rankine cycle, the efficiency is given by these expressions that we've already seen. So we can start out, we can actually decide that we want to find all the enthalpies and use them. Or we can decide that we want to find the Q out and the Q in and use them. Or we want to find the W turbine and W pump. Which one whichever one will be easier for you to work with in your question, right? So we can start out by finding the work of the pump. And remember we said it is V1 P2 minus P1. We are working with water, so this is the example I was saying, that the density of water is 1000 kilogram per meter cube. It's going to be fairly constant over the a range of pressures, right? So if I'm going to compress it, then it means that my specific volume is 1 over my density. So that's 1 over my 1000. That's where I got the 0.001 from. So that's here. And then P2, we need the units to be consistent. And it's advisable that you keep it in kilopascal. So 2000 minus 10, right? And then your specific volume should be in meter cube per kilogram. So when we do that, we get this value for the work of our pump, right? So that's all I was just saying here, that we assume a constant density of water. So our specific volume is just 1 over our density. Now to find the work of the turbine, we need H3 and H4. But from the question, we have H3, we don't have H4. So if we look at it here, the diagram was given to us. We have H3 to be 3248 kilojoule per kilogram. If it wasn't given, right, we would read it as the temperature and pressure. So we know the temperature and pressure at point 3, that's 400 degrees Celsius, 2 megapascal. So we'll go to the superheated steam table and read the enthalpy there at those conditions, right? So that's what we would do. Okay, I think I'll mention this later as we go on. So we have H3, but since it's a cycle, we will start from the points we know and work our way to the points we do not know. So you realize that we said there's a relation. So this is the thing about the thermodynamic cycles, right? You look at the points where you have enough data and you use them as a starting point to find the data for the other points. So that's how we do it. We work from the known to the unknown. And we look at the relations between the points. So we know that, for example, right, from points 1 to 2, we said it is isentropic compression. That means that they have the same entropy, right? From point 2 to 3, we said it's a constant pressure heat addition. So they have the same pressure. From 3 to 4, isentropic expansion. So they have the same entropy. 4 to 1, constant pressure heat removal. So they have the same pressure. So we know the relations between them. Now, if 3 and 4 have the same entropy, then it means that the entropy at point 3 will be equals to the entropy at point 4. And this is a very important point for our calculations, right? So let me clear the screen. So what we are saying is that we know that from point 3 to 4 we have isentropic expansion. So it means S3 is equal to S4. Once again, S3 was given to us in the question over here, right? So in the case that it wasn't given, we would have read it still from the superheated steam table at the 400 degrees Celsius and the 2 megapascal. Would have read that value. So we have examples where we would actually read. So I'll take us through those ones as well. So it means that S3 is equal to S4. Now we can use that to find H4, because remember that when you are dealing with um, um, something like water and steam, right, you need two parameters to be able to determine the other properties. So usually if you have temperature and pressure, you can find anything else. In the same way, here I have entropy and I have pressure. So I can find everything else I need to find, right? I can find everything else I need to find. So we know the entropy at point 4 to be 7.1279. If we should check, we also know the pressure to be 10 kilopascal. So if we should check at 10 kilopascal, what we are going to see is that this is 10 kilopascal here. We are going to see is that the entropy of 7 points, the value again, 7.12, right, is in between SF and then SG. So it means that it's a saturated vapor liquid system. Right, so remember, if your value is in between SF and SG, you're a vapor liquid mixture. And when you're a vapor liquid mixture, we have to find the quality. So it's a quality that will help us to find the enthalpy. So take note of that. For the Rankine cycle, when you are looking for the properties at point 4, you are a saturated vapor liquid mixture. So I said that previously. You're a saturated vapor liquid mixture. So that's what I was saying over here, right? That it's a saturated vapor liquid mixture. So that's over here, right? So if it's a saturated vapor liquid mixture, you need to find the quality, and we use the quality to find the enthalpy. So this is a formula for our quality, right? And what I'm saying here is we may need to use the steam table to find the enthalpy. So when we check the tables at 10 kilopascal, and an entropy of 7.1279, we realize that the fluid at point 4 is saturated. It's a vapor liquid mixture. So we can find the quality. So we just make x for the subject, right? So we have S4, that is the entropy we calculated, which we said was equal to S3. We can read SF and SFG from the steam table, make X for the subject, and we can use that to get our quality. That's 0.865. Then from there, we know our quality. We can use the same relation to find our enthalpy. So we need H4, right? Using the same pressure, the 10 kilopascal, we can read HF, HFG, and use that same quality. When we put in the values, we will get this to be our enthalpy at point 4. Now we can find the work of the turbine, H3 minus H4. So we just put in the values and we have that to be the work of our turbine. Now you realize from the efficiency formula that we also need to find Q in, because we said it is work of the turbine, right? So we said it's work of the turbine minus work of the pump over Q in. Yes, to be our efficiency. And Q in we said was H3 minus H2. So we do not know H2, but once again it's a cycle, right? So we can start from a point we know and we can use it to get to a point we do not know. So we know the pump work at point 1, right? So we know the work of the pump at point 1. Remember we said that the pump work was H2 minus H1. So we know the pump work, and H1 was given to us in the question. Once again, in the case that it is not, we can go to the steam table. We are going to read the value of H at the given pressure, right? And it's going to be a saturated liquid, so HF. Because we said at point 1, usually we are a saturated liquid, unless otherwise stated in the question, right? Unless the question gives you a temperature and pressure. If the question gives you just the pressure, take it to be a saturated liquid, right? Or if the question states otherwise. So you can read your HF or you can read your H at point 1 based on what the question says. But in this case, it's a saturated liquid, right? So we are just going to use, H1 is going to be equal to the enthalpy of a saturated liquid at the pressure, which was the 10 kilopascal. So if we should read that, we'll get, let me clear the screen again. If we should read that, we'll have our H1 to be 191.8. It was given to us. We know our pump work which we calculated, so we can make H to the subject. Then we can put that in the Q formula here and find the Q in. Then from there we can just put in all the expressions into our efficiency formula, and that becomes the efficiency of our cycle, right? So now notice that because the pump work is so small, there are times that we can neglect it for our calculations in finding our H2. So if there's a case where the pump work is very, very small, sometimes we are allowed to neglect it to do our calculations, right? That's if you don't have enough data. You can consider that for the purpose of simplification. But almost all the time, you will have enough data to find your pump work. So don't neglect it. Almost all the time, you have enough data to find your pump work. So if you can find it, please find it and add it. There are some cases where it will not be negligible. So we have a question where the pump work was very high. So let me just skip there to show it. We'll come back to all these questions today. But I think that was the last part of this. So that we can see an example where we can't just neglect it. Sorry. I think I went too far. Good. Over here, the pump work is about 15.1399. Right, the pump work is about 15.1399. This is not negligible. It has a significant contribution. So in a case like this, neglecting it, making the assumption and just neglecting it will be a very risky move. Okay, so we can go back to the main slide. I think we are done with the first question. Let me make sure I didn't leave anything out. Okay, so we are done with this one. We can go back to the main slide. So that's it for this question. So that was for the ideal Rankine cycle. But for a real Rankine cycle, what's going to happen is that there will be some kind of losses, right? So there will be pressure drops, there will be heat losses, there will be irreversibilities. So it means that instead of us moving So the broken lines are the real thing. So instead of us moving from 1 to 2 along the solid line, then 2 all the way to 3, and then back down, and then this way, realize that we can't do that. So if you look at it carefully, you see that for the real Rankine cycle, from 1 to 2, right, it is not isentropic. This part was isentropic, but 1 to 2 is not isentropic. There's a little change in entropy. So this is the entropy axis. You can see a little change in entropy. 3 to 4. So if I take 3 down and I trace 3 down and I trace 4 down, there's a change in entropy. So it's no longer going to be isentropic. It means that for us to find the actual work of the pump and turbine, we need to use the isentropic efficiencies, right? So isentropic efficiencies relate the isentropic efficiencies relate the actual work, sorry, relates the actual work to the isentropic work, right? So the isentropic work is the work that we are expecting if it was a constant entropy process. Another thing is that the heating is also not so straightforward. So there are some heat losses to the environment and all those things, right? So we have an example here that a Rankine cycle operates between pressures of 2 megapascal and 10 kilopascal with a maximum temperature of 800 degrees Celsius. If the efficiency of the turbine is 87% and the isentropic efficiency of the pump is 85%, determine the thermal efficiency of the cycle. So let's go to the part where I've solved the questions. Right, so we have here the same question. Determine the thermal efficiency of the cycle. The question is quite similar to what we've already done, but then this time we are going to account for the irreversibilities. So it is the same formulas that we use, right? But then there are a few new formulas for us to note. So we see these formulas from our discussion on entropy. The isentropic efficiency is given by this formula for a turbine, and for a pump is this formula. So please do not mix them up. The way I remember it is that usually efficiency is supposed to be output over input, right? So I'm trying to build up on something. For a turbine, what we are going to produce, what comes out of a turbine is work, right? So it means that since the turbine is going to be producing work, right, that's going to be the output. So it means that it is going to be the actual work I'll have up here because it is producing the work, right? So it's going to be the actual work at the top over the isentropic work. But then for a pump rather would use the work. So the actual work becomes the input. So for a turbine and a pump, I look at what they do. Since the pump is going to be using the work, then the actual work that is going to be done on the system is going to be an input for the pump. So for the pump, it's going to be the isentropic over the actual, right? And then for the turbine, the actual work that will be done by the turbine is the work that would be coming out. That's the output. So it becomes W actual over W isentropic. So that's what I used to remember it. I don't know how else you may want to memorize it, but if there's another way you can memorize it for it to work for you, then that is fine. Then we see here H3. So it was supposed to be H3 minus H4. But then this is the actual H4, and this is the isentropic H4, right? So the isentropic ones are like what we did previously. You read the entropy, find the quality, right? Then you use that to find the enthalpy. So the same thing goes for the pump. So the isentropic enthalpy at point 2 and then the actual enthalpy at point 2. Okay, so we need to find the actual values at every point. So at point 1, once again saturated liquid. So we can read this from the steam table. So let me open up the steam table. I think let me split this screen so that we can see it. So at point 1, we are looking at 10 kilopascal in a saturated liquid. So we look for the steam table part that works with pressure. 10 kilopascal is here, right? So let me highlight that whole row. Now, if we want to find the HF at that point, HF is here, so that's the 191.8. So that's how we came up with this value, right? And we also need the entropy so that we can relate it to point 2. So I'm going to show us another two ways to do things. So since it's going to be isentropic, we can find the entropy at point 2, right? Because between 1 and 2 is isentropic. So I can find the entropy at 1. So that's going to be my SF. That's the 0.6492. And it will be the same as the entropy at point 2, right? Then at point 2, the pressure there is now 2 megapascal from the question. We're told that the um, the upper pressure, the higher pressure is 2 megapascal. So that's from 2.2 and point 3. So we know the entropy, we know the pressure. So we check our steam tables to see if we find something like that. And then the problem is that, remember we said that at point 2 is compressed liquid. So if we should check the compressed part of the steam table, so that's here, the compressed part of the steam table, right? Realize that we don't have up to 2 megapascal. 2 megapascal is way below what we have in our system. So that's what I was just trying to say from this slide, that we can't find the value easily. So it means we need a different approach, right? So what we are going to do is that we are going to use the formula V P2 minus P1 formula for the pump, right? Would use that formula. The other things I was saying on this page was that, remember we found the entropy to be this and then the pressure to be 2 megapascal. If we check the pressure of 2 megapascal, not from the compressed part, right, realize that our entropy is way lower than the entropy of a liquid, which is the one I highlighted in green. So if your entropy of your liquid is 2.4, right, and what you have is less, then it means you are compressed, right? Because entropy is a measure of randomness and disorder. Gases are more disordered than liquids, right? And liquids are more disordered than compressed liquids. So if my entropy is reducing, I'm moving from liquid to compressed liquid. So this is just something that I put there for us to take note of. So another way we can look at the isentropic efficiency for the pump. Remember we said it's going to be the isentropic work of the pump over the actual work of the pump. And we said the isentropic efficiency can be written as this. But then from the calculations that we did in the previous example in question 1, we were able to relate it to this. So this formula here is for isentropic work done, right? So I can just find that work. I know my specific volume, I know my P2 and P1, right? So I can just put them in there, and then yes, I can now make the W actual the subject. So if I make it a subject, then the efficiency now becomes the denominator here, right? Then I can just put in the value. So I know my V, my P2, my P1, and then my efficiency. I can find the actual work of the pump. Now let's consider the turbine. So the turbine at point 3, we are looking at the entropy at 600 degrees Celsius and 2 megapascal. So 2 megapascal is 2000 kPa. So that's what we have here, right? And if we check the temperature, you realize that the temperature that it will be saturated is 212.38. It means that at the 2 megapascal or the 2000 kilopascal, we need a temperature of 212, right, for it to be saturated, for it to start becoming vapor, right? But then our temperature is way above that, so it means that it is definitely going to be a vapor. So we are in the superheated region. And remember, we said point 3, we are in the superheated region. So at the superheated region, I can look for my 2 megapascal and then my 600 degrees Celsius. So I highlighted it, and I can find my entropy. So that's the value we have here. So that's what I've written over here. And we also need the enthalpy. So the enthalpy is over here, right? Still at 2 megapascal and 600 degrees Celsius. So we can find the enthalpy. So remember, this is a separate table, the one up here. So the enthalpy is this column. Sorry, the enthalpy is this column, and then the entropy is that column, right? So we can read the enthalpy. Now, since from point 3 to 4 we have isentropic expansion for the ideal case, S2 is equal to S4, so we can find the enthalpy at point 4 for the isentropic case. So we use the same approach we did. We have our S4, we know the P, right? So we are coming to read at 10 kilopascal and at an entropy of 7.7. We are in between the SF and then the SG. Let me zoom it in. So we are in between SF, which is 0.64, and SG, which is 8.1. We are 7.7. So it means that we are a saturated vapor liquid system. So we'll find our quality, right? So the same approach, as what we did previously. We find the quality. We use the quality to find the enthalpy. So we read our HF and then our HFG, find our enthalpy for the isentropic case. Remember, this formula or this approach was used for the isentropic case. Now we can find our isentropic efficiency. We can find the actual enthalpy using the isentropic efficiency. So I have the formula for my isentropic efficiency. I know the value from the question. They said the efficiency of the turbine was 0.87 or 87%. I know my H3, which I read. I know the H4 for the isentropic case, which is this. So I just make the actual the subject H4A. This will be my actual enthalpy at point 4. So the actual turbine work is H3 minus H4, and that will be this value over here. Now for the efficiency of the cycle, right, we said is the work of the turbine minus the work of the pump over the Q in. And we know the work of the turbine now, we've calculated it, the work of the pump, we calculated it. But Q in we said was H3 minus H2. And remember, we said H2 is equal to the work of the pump plus H1. So what we are going to do is that we are going to find H2. We'll take the work of the pump, the actual pump work, right? If we use the isentropic pump work, we would find the isentropic efficiency at point 2, right? So if this was the isentropic pump work, if we want the actual, if we want the actual H2, then we need to use the actual pump work, then plus H1. So that's what we've done over here. So we just put in the values. Let me clean this. So we just put in the values, then we can find the efficiency of our cycle. Okay, so I'll go back to the slide once again, the main slide, and then we would I think we should be wrapping up very soon, and then I'll make the other video separately. So now we are saying that how can we increase the efficiency of the Rankine cycle? So the high efficiency plants, if you have a plant that has a very high efficiency, it means you have more profits, right? And there's a better fuel efficiency and better impact on the environment while you're generating your electricity when you have a very highly efficient plant. So the basic idea behind all the modifications you do is to increase the thermal efficiency of the power cycle. And to increase the thermal efficiency, there are a number of things we can do. We can increase the average temperature at which heat is transferred to the working fluid, or we can decrease the average temperature at which heat is rejected. So all we are saying is that instead of us heating it to 0.3, we can heat it to 0.3 prime. And when we do, the heat increases by this amount, right? Or the efficiency, increases by or the increase in efficiency is proportional to this amount here. In the same way, instead of us cooling it or expanding it with the turbine to 0.4, you can expand it to 4 prime, right? So it's at a lower temperature now. We are going to remove the heat at a lower temperature. So what's going to mean is that the efficiency is also going to increase in relation to this magnitude over here. So all we're just trying to say is if you have higher temperatures, right, for your at point 3 for your superheated parts, you are going to be more efficient. And if you have lower temperatures after your turbine, you are going to be more efficient. But these come with a lot of issues themselves, because having very high temperatures may not be suitable for your equipment, and having very low temperature openings too can cause this to enter the vapor liquid region, right? So your turbine might have issues once it is still along that path. But then there's another thing we can do. So we can also increase the pressure of the boiler while we keep the temperature constant. But then the issue with this is when you increase the boiler pressure and keep the temperature constant, you would rather end up causing more liquid to form. So instead of it to be superheated, you might end up having some liquid droplets in there. Because think about this, I have water, maybe let's use the practical example, the very common example, water at 100 degrees Celsius and then maybe at 180, we know that it will become a vapor, right? Now I'm keeping the same temperature and I'm increasing the pressure to maybe 280 atm. What's going to happen is that because I'm increasing the pressure, I'm going to force the the molecules closer together, and so liquid will start forming. So when we increase the pressure of the boiler and keep the temperature constant, it's not going to be too reasonable, because we would end up having some kind of liquid forming, and that's not good for our turbine, right? So you can increase the pressure, it would increase the amount of work from this part here, but it's going to decrease the amount of work at this part over here. Okay, so we have an example of that. So this is going to be our last example, and then we'll look at the reheat later. But the whole idea of the reheat is, so I'll just brush over it. When I'm doing the next video, I'll still talk about it. The idea of the reheat is, after we get to point 3, right, we can start some kind of expansion. So there will be some work that we are doing here. Then we heat it again, right, and expand again. So I'll discuss the formulas in the next video. So let's look at the last question we have, and then we can wrap this up. So this is our last question. We said that consider, sorry, okay, I think I have time. So consider a steam power plant operating on the ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius, and it is condensed in the condenser at a pressure of 10 kilopascal. So you're supposed to determine the thermal efficiency of this power plant, and the thermal efficiency if the steam is superheated to 600 degrees Celsius instead of the 350. Then the thermal efficiency if the boiler pressure is raised to 50 megapascal while we maintain the inlet temperature at 600 degrees Celsius. So what we are saying is, what the question is saying is, once again, let me just, so we have here our pump. This is point 1. So I'll just use the temperatures and pressures. Then we have here our heater. We have here our turbine. Then we have here our condenser. So the first part of the question is, we have the low temperature part to be at 10 kPa, the high temperature part to be at 3, so high pressure part 3 MPa, and then it enters the turbine at 350. So into the turbine is going to be the high temperature. So this side is at 350 degrees Celsius. So what we are saying is, first we should find the efficiency for this cycle. Then we should find the efficiency if this is not 350 but 600 degrees Celsius. And then after that, instead of us having this to be 3 megapascal, we want it to be 15 megapascal. So basically, we are going to do the same calculation, but we are just changing temperature and pressure reading from different parts of the steam table. For the first part of the question, we want to work with steam entering the turbine at 3 megapascal and 350 degrees Celsius, and it's condensing in the condenser, not in the condensing, sorry, in the condenser at 10 kPa. So we'll find the efficiency with our formulas. So we can first start by finding the pump work. So we know our V to be good. So this is the part where I showed the two examples. So if we use the 1 over rho, right, we'll be working with this value, and this is the work we'll be getting. But I was saying that note that we could equally have read the value from the steam table at the 10 kilopascal. So that's going to be the VF, saturated, the specific volume of the saturated liquid at 10 kilopascal. So after pumping, it becomes a compressed liquid, and the specific volume is almost the same, right? So we can just use the VF at the temperature or pressure given to us in the question, or we can use the 1 over rho. But once you can read it from the steam table, read it from the steam table. So if I should open up the steam table, right, at 10 kilopascal, our VF is 0.00101. So that's what we have here, 0.00101. So that's the value that we would record. And when we rather put this into this formula, our W is 3.0199. So that's what we would use for our calculation, right? So read VF at the saturation pressure. I feel like that's better, right? And then you would use it for your calculations throughout. So as I said, I personally advise to always refer to the steam table and use that value if you can to be on the safest side. So now we need to get our enthalpies at a point so that we can also read we know we will need our enthalpies at a point, so we also need to read HF at that point. So from the same steam table, we can read HF at 10 kilopascal, and we'll get 191.8 kilojoule per kilogram, and we can move on to find H2. We know H2 is the work of the pump plus H1. So I know the work of my pump, I know my H1, can find my H2. Now we know H2 and we know P2. We can move to point 3. We know that P3 and P2 are the same, consider that they are having the same pressure, right? And we know T3. So we can go to the superheated table, read the entropy and then the enthalpy. And here I was asking why entropy, because you know it's isentropic and we need to relate zero point 0.3 to zero point 0.4. The thing relating them is the entropy. So we've seen that a number of times. So I can read H3 as 3 megapascal and 350 degrees Celsius from the steam table. So if I should come to the steam table here, right? So this the first table here is for the saturated water, but we are working with the superheated. So as a 3 megapascal, so you can decide to ignore this. I wanted to use it to explain something, but I don't think you would need to worry about it because I've said it a number of times. So at the 3 megapascal and then at the 350 degrees Celsius, we have our enthalpy and our entropy. What I was going to say was that if we look at the 3 megapascal, which is 3000 kPa, the saturation temperature is 233, but our temperature is higher, so it means you're in the superheated region. But we already know that at point 3, we are in the superheated region, so we don't really need to stress with that. So that's what I was just saying here, that they are higher than the saturation temperature, so we are in the superheated region. And we should note that usually at point 3, we are in the superheated region. So we just go to the superheated table, read 3 megapascal, 350 degrees Celsius, find our enthalpy, then our entropy. Then we know that the entropy at point 3 is equal to the entropy at point 4. So now we can come back. So we know at point 4, we know the entropy at point 4, we know the pressure at point 4, which was equal to the pressure at point 1. That was the 10 kPa. So I can come back to the 10 kPa and then compare the entropy values. My value is in between the SF, that's for the liquid, and then the SG for the vapor. So I find my quality. So please keep these steps in mind, right? Isentropic, you find S2 is equal to S4, you find your quality, use your quality to find your enthalpy. So now I know my H4. Then I can just put all these values in, right, in my expression. So I can put them into this expression, or I can use them to find the W turbine, W pump and Q in, or I can put them in this expression, or I can use them to find, remember, H4 minus H1 is the same as Q out, H3 minus H2 is the same as Q in. So I can use any of these expressions, put my values in, get my efficiency. Now we want to work with 600 degrees Celsius instead of 350. So it's the same steps, right? Point 1 and point 2 are going to be the same. For point 3, instead of us reading at 350 degrees Celsius from the steam table here, right, so we rather read at the 600 degrees Celsius. So we'll be working with this enthalpy and this entropy. So this becomes our S3, right, which is also equal to our S4. That is 7.5103 kilojoule per kilogram Kelvin. Then we'll just do the same thing and find our quality. So I left the answers here for us to try out. The enthalpy are 3, the entropy are 3 and 4, the quality. So you can do it and confirm your answers, right? Then we can find the enthalpy at point 4. So after we find the quality, find the enthalpy at point 4 with all the things we've done so far. And then the efficiency of the cycle should be this. Then the last thing is that we are now looking at a change in the boiler pressure. So now instead of us using 3 megapascal, we are using 15 megapascal. So this is going to affect point 2 and point 3 because now it's the boiler pressure that has changed. It means that from point 1, after I pumped it, right, instead of it coming out at 3, should that coming out at 15, goes through the boiler, right, and it's at 15. So it's no longer at the 3, it's at 15 now. So I have to find my value for point 2 as the 15, right? Or I have to find the pump work. Remember the pump work was V P2 minus P1. Since P2 has changed, the pump work would also change, right? So I'll need to find all those new things. So once there's a change in point 3 as well, there's also going to be a change in point 4 because they're related by isentropy. So we'll find a new H2, H3, and H4. H1 is the same because the pressure there didn't change. So it's still the HF at the 10 kPa. So now let's find our work of the pump. So we use this formula now. Instead of it being the 3000 kilopascal or the 3 megapascal, we're using the 15 megapascal or the 15,000 kPa. So this becomes our work. In the same format, H2 is the work of the pump plus H1. So we can find our H2. Then H3, now we read at 50 megapascal and 600 degrees Celsius. So if we should check the steam table, 50 megapascal and 600 degrees Celsius, so that's superheated. So we know it's going to be superheated. So I look for 50 megapascal, I look for 600 degrees Celsius. So that's here, right? The values are the 3583 and the 6.6796 for the enthalpy and then the entropy. So we can take it from there. So we can read those values H3 and S3. But remember, S3 is equal to S4. At point 4, we know S4 and P. So P4 or P1. So P4. We can find our quality, find our enthalpy, put our expression in, and find the efficiency of the cycle. So try out the questions from um, the tutorials, and then I'll make the video on the so the next video is going to handle from the Rankine cycle with reheat. So I'll talk about it, and then the combined cycle. Then when we are done with that, I will make another video for the last thing we have to do, and that's going to be on the refrigeration cycles. So we'll talk about all these things, and then we would be done with the thermodynamic cycle. So thank you for your time.